Singh, Dean Academics Dr. Navjeet Sharma, my dear colleagues, and all the participants. I feel honored to extend a warm welcome to each of you on behalf of organizing committee for our two-day national conference on frontiers in theoretical and experimental physics, sponsored by Department of Biotechnology, Government of India. As we prepare to embark on the second day of the event, I kindly request everyone to please rise for DAV class.
अविरल निर्मल सलिल सदय ज्ञान प्रदायिनी ज्योतिर्मय हो चहु दिशि उद्घोष अभय दिए विजय जय दिए विजय जय प्रबल प्रवाहमयी नित नूतन जीवन दायिनी सदा सनातन वेद प्रणीता परम पुनीता हे धारा अक्षय दिए विजय जय दिए विजय जय दयानंद से प्रेम भक्ति ले हंस राज से त्याग शक्ति ले धर्म भक्ति का राष्ट्र शक्ति का हो दिन मान उदय दिए विजय जय दिए विजय जय सुख समृद्धि इसकी लहरें प्रेम शांति इसके तट ठहरे सघन शांतिमय प्रबल कांतिमय लिए अटल निश्चय दिए विजय जय दिए विजय जय.
Thank you. An experiment is a question science poses to nature, and measurement is a recording of nature's answer. With that spirit, let's continue to keep questioning and exploring. Before we start our second day schedule, let's take a quick look back at the highlights from yesterday's sessions, which includes one keynote session by Dr. Mukesh Kumar, two invited talks by Dr. Sunil Bansal and Dr. Rohit Mehra. Dr. Mukesh Kumar spoke on solar blind photodetectors, an emerging technology with promising applications in forest fire detection, territorial intrusion monitoring, ozone hole assessment, deep space exploration, satellite systems, and secure communications. Dr. Sunil Bansal provided an overview of particle physics, tracing the historical path of experimental breakthroughs that has shaped our present understanding of the material universe. Dr. Rohit Mehra discussed the occurrence, sources, and biokinetics of uranium in the human body, supplemented with the case studies highlighting contamination levels reported in different regions of India. Each session has been a building block towards a broader understanding and more impactful solutions. So now we are pleased to welcome Dr. Hitesh Sharma, Registrar and Professor at NIT Delhi, and Dr. Harpreet Singh, Assistant Professor in Physics, Department of Physics, Guru Nanak Dev University, Amritsar. I now invite all the esteemed dignitaries on the dais to come forward and present a token of our sincere gratitude to our guest speaker, Harpreet Singh and Dr. Hitesh Sharma. now time to commence the first session of the day, which will be delivered by Dr. Harpreet Singh. To formally introduce Dr. Harpreet Singh, I would now like to invite Dr. Navjeet Sharma to the dais.
Good morning to all present. So now I formally introduce the first speaker of the day, Dr. Harpreet Singh. Dr. Harpreet Singh is an assistant professor in the Department of Physics, Guru Nanak Dev University, Amritsar. He received his PhD in physics from the Indian Institute of Science, Education and Research, Mohali. His research expertise spans quantum sensing, quantum computing, NMR spectroscopy, and quantum technologies. Dr. Singh has significant international research experience, having worked as a postdoctoral fellow at the Technical University of Dortmund, Germany, and at the University of California, Berkeley. He has published extensively in research journals. His contributions include pioneering work on room temperature quantum sensing and organic crystals, multi-photon transitions in silicon vacancies, and quantum state protection using dynamical decoupling. He has also presented his work at prestigious platforms such as Experimental NMR Conference USA, European Congress on Magnetic Resonance Prague, and Nuclear Magnetic Resonance Society Symposia in India. He is also an active reviewer for the various APS journals, Nano and Nano Letters, and currently his work focuses on developing advanced quantum sensing techniques using doped organic crystals for high sensitivity layers.
Thank you so much, sir. Let's now invite our guest speaker to take the stage and begin his session on the fascinating topic, quantum sensing using doped organic crystals. So I invite Dr. Harpreet to start his talk.
Okay, so thank you very much for such a nice introduction. So let me start. As in the introduction they told that I'm going to talk about the quantum sensing using doped organic crystals. But the question is why now? Like we start talking about quantum technologies. Like what changed? Like a few years ago we were talking about classical, everything is like we are racing and we have very high sensitivity everything. But where we are lagging and what is like what is the next and what is the motivation why we want to go into the quantum. So being a physicist, I think quantum mechanics is not new for us. Like it is introduced in our, so we already study in our syllabus. Okay, and we know like the world after 10⁻⁹ meter is a world which can be explained only by the quantum mechanics, and classical mechanics cannot explain it. Okay, so this is like the motivation for the physicists to do quantum mechanics. Like we want to know that how the subatomic particles behave and all these things. But nowadays, like computer scientists also start talking about the quantum technologies and quantum. Why we are got interested? The answer is that this Murray law. So Murray law is simply that first we say that every year the transistor will be double on a chip, but now like after that they modified every 2 years the transistor will be double on a chip. But now we are already reached a regime where the transistor size is in nanometer. It's like 4 nanometer, 7 nanometer, and this is the boundary where the quantum starts. Okay, so now the computer science people are also talking about the quantum computer, because if you make the transistor size less than that, you have to play with the quantum mechanics. Okay, so there are some phenomena which occur. For example, quantum tunneling is a very important factor, which is a problem, maybe problem for the transistor action. Okay, so this is why this computer scientists are interested in quantum computers and quantum technologies. Now, for the kids, like why we like what is the difference between the classical and the quantum world? So classical world, you know, we are living in this world, and this is very familiar to us. We have X, Y, Z, and three-dimensional space. And if you want to talk more about, you can add the vector four space also, time axis. But yeah, means for the common people, I think we are very much familiar with this 3D space. Okay, so everything which is here we call it real. Okay, and how the quantum world is different, we have a Hilbert space. I think Hilbert space, everybody know what is Hilbert space. So Hilbert space is a complex space. Okay, so these atoms and particles of less than size 10 raised to power minus 9 live in this space. Okay, and what we see in the real space is a projection. Okay, and the projection, what we call, is like something which can be represented by the wave function. Okay, so this is what we learn in our DSC and MSc exam. So this is something which you people already know. Okay, now like how to represent a quantum state. If you have like one spin system which have a two state, so what is the difference? So that spin can be represented by a so here that is missing, sorry for that. But if you have this general state, that can be represented in a 3D space, okay, on a block sphere. So this is something new. So basic idea is that this is a complex number, this is also a complex number, and here you have one relation. So this is a one constraint. So total variable in this equation is 4. Okay, but this quick constraint making it 3. Okay, so it means that if you have a spin in a Hilbert space, you can represent in a real space with a three-dimensional real space. Okay, so basically one spin can be represented like this. So this upper is like 0 and this one is 1, and anything can be in general like this. Okay, so this space is this block sphere is called block sphere, and in general state of two-dimensional or one-dimensional Hilbert space can be represented by this. Okay, two-dimensional Hilbert space can be represented on this in this real space block sphere. Okay, so now how the classical bit and quantum bit is different. Okay, so basic idea is that we know in our computer we have bits. Okay, so one is 0 state, another is 1 state. So if you have a voltage below the certain logic, certain level, then we call it 0, and if it is 1, if it is above that voltage, then it is 1. Okay, so this is called bit. But in quantum, we have a qubit. So it's a quantum bit. So quantum bit have a property that apart from 0 and 1 cat, you will have a superposition, alpha times 0, beta times 1. So basically, this is the difference which is not present in the classical computer. Okay, so here you have certain advantage of superposition which you can use. And for example, you can write an algorithm such as Grover search algorithm. So Grover is an Indian scientist. He was working in IBM, and he was like the person who actually part-time working on the quantum. And he found that you can use the superposition principle which you are learning in your BSc or MSc, and you can write an algorithm and by which you can do the search fast. For example, the classical search if you do on a Google, if you have like 100 unsorted data, you need 50 iteration. Okay, but if you do the global search, you just need 10. Okay, so that is the advantage of the quantum computers. Okay, so this is a motivation. Okay, like you can use this phenomena of which exists in the quantum world, and you can bring it into the classical world and use it for the search. Okay, so this is the something which motivates the pupil. And there is a one more algorithm, that is Shor algorithm, which you can factorize the prime number. But these are the things which basically you cannot do actually on a classical computer, but because quantum mechanics giving you that freedom and you can do that. Okay, so these are the things which motivate like why we are now looking towards the quantum technologies. Okay, and another difference is like in classical we have 0 and 1, but in quantum bit if you measure, you always get 0 or 1. Okay, like if you have you are in the state of alpha times 0 and beta times 1, but when you measure, you will either get 0 or 1 with the probability alpha square and beta square. So here something which is little bit strange, I will say, and which was not digested by Einstein. He said that God is not playing in the dice. Okay, so this is a very famous statement. So this measurement problem is like why when we measure the state collapse to the one particular 0 or 1 when it is in superposition and give us some probability. So that was the something which you could put doubt on that whether it is correct or not, that this theory. But later on, I think we all know this is a journey like a EPR paradox. He introduced paradox, and then Bell come up with an inequality. If this inequality is violated, then the quantum mechanics is right. If not, then something wrong. Like there may be some hidden variables which are missing, and that's why we are coming with a probability. But later on, these three scientists did experiments, and they proved that actually the quantum mechanics is correct. Okay, so the idea is that this guy is actually from UC Berkeley, and he was doing postdoc. So he was very motivated to testify the quantum mechanics, but most of the professor told him don't do that, otherwise you will not get a permanent job. But he said, okay, I will not get a permanent job, but I want to testify that. And in Berkeley, like when I was in Berkeley, people tell me the story that generally what they do, basically whatever the instrument is not required, they just write it is useless, but maybe closer can use it. Okay, but he did all the experiment using all the waste. He did not have funds to verify this, which is very important theory. But this was this guy's hard work, and the result was like he did not get any faculty position, so he was nobody till 2022. But when he got Nobel Prize, now everybody knows it. Okay, so sometimes if you are really motivated, you still face some problems. Okay. Okay, so these are the quantum resources which are available. So if you want to build a technology, now you know quantum superposition, there is a quantum entanglement, which is higher order superposition, I will say, for simplification. And then quantum measurement, you know, like it is different, it do not exist in the classical world, but in quantum, if you measure, you will get 0 and 1. And another is quantum contextuality and quantum tunneling. So these are the resources available, and we already know about it. Okay, so now we are in the era of third revolution of the quantum technology. So the idea is that here we use all the quantum mechanics and build the technologies, and these are the resources which you have to use, and you know what is all these things, and just use that and improve what we are doing in our daily life. So this is what the quantum technologist is doing right now. So maybe in future you guys can be a quantum technologist if you just use these things and convert it into something useful which you are doing in your daily life. Okay. But the biggest obstacle is this difference. So basic idea is whatever the quantum effects are there in the quantum world, when the system gets bigger and bigger, this coherence is scaled. So these quantum properties are actually die out. So this is the obstacle. So most of the people are fighting with that. Okay. So if you want to you want to do something quantum, you want to use quantum resources, this is the obstacle. Okay, so you have to find out the way to stop the decoherence. So this is the limitation which you have to mitigate in your system. Okay, so this is a brief chart. Like the first quantum revolution happens in the 20th century, and I think you already know, like wave mechanics, Schrodinger come up with the Schrodinger equation. And then the second revolution came where we talk about the quantum dynamics, Feynman did a lot of things, and people start talking about superposition, decoherence, quantum computer, and spin manipulation. So these are the in the 21st century. But now we are in 22nd century. So 22nd century, we are in the third revolution. So as I told you, we have to use all the quantum resources which I listed and convert it into the technology. Okay, so these are the two major fields which I am interested in, and right now I'm working from last 10 years. One is quantum computing, another is quantum sensing. So maybe in this talk I will focus on the quantum sensing only. Okay, so what is quantum sensor and what is quantum sensing? So basically, like you know, you have some classical sensor, for example this video, right now recording, it is capturing the light and converting it into the digitalizing it 0 and 1. Okay, so the answer question is that can we improve the sensitivity of this? That is the question. If we use instead of classical sensor or classical phenomena, can we use quantum sensor and improve the imaging? So that is the thing which quantum sensor is actually we are doing. So one of the important candidates is NP center in a diamond. So NP, you know diamond, everybody know diamond. So diamond is carbon, carbon, carbon. So if you remove one carbon and put a nitrogen and remove one more carbon, and then the vacancy and is followed by a nitrogen, is give us a center which is a defect in the diamond and it emit a fluorescence. Okay, so this center have a very nice property. If you shine a green light on it, what will happen that if you shine it for a sufficient time, all the population is actually go to the excited state and then come back preferentially to the zero state. Okay, so then what will happen that it gets spin polarized. Okay, and it gets spin polarized and you can use this system for doing the quantum sensing. Okay, so now what you know, like if you have this level and if you apply a magnetic field, you know Zeeman splitting happen. You did in BSc and MSc and all this thing that when you apply a magnetic field to the atom or this is also by the way we can call it artificial atom. So this system is act as an artificial atom, and then we apply a field. What will happen? That split happen. Okay, and that split. And if you apply, there is a technique called optical magnetic resonance. So basically, you will change when you apply the magnetic RF. You can change the population of these levels, and when these levels population change, the emitted fluorescence also change. And if you record that, you will get a peak. Okay. So the idea is that whenever we apply the magnetic field and this splitting happen, and when this splitting happen, these peaks get split, and we will know the that effect of the magnetic field, and the vice versa. Like if the magnetic field is present, then these peaks get split. Okay, so basically we can use it as a magnetic sensor. Okay, now the question is that how better it is. See, the diamond is a very strong. Okay, if you want some sensor in a really extreme condition where you want to measure magnetic field. For example, if you want to measure a magnetic field at 500 degrees Celsius. So there, like the normal sensor, like Gauss sample, Gauss meter or something may be difficult to use, but here you can use this, okay? And or under a very high pressure, you want to measure the field, or you want to measure the pressure only. So basically, your Gauss meter can break, but this kind of sensors work, okay? And also this is very sensitive sensor. So this I told you how to measure the DC field, like how to if you apply a DC field, but you can measure the AC field also. So here little bit complex pulse sequence you will use, and but the idea is that you apply some pulses and manipulate the spin state and apply the AC signal, and when it is at right frequency, you will see the dip in a signal. Okay, and that dip will tell you that what is the frequency. So basically, you can measure the AC field also using this kind of sensors. Apart from that, not only like in normal fields, you can make a nano diamonds, okay, and it have a NV in it, and you can actually put in a single cell. Okay, so the nano diamond, the cell of our cell is at 10⁻⁶. You can put it in the cell, and then you can measure the temperature and magnetic field and all these things into the cell also. So this kind of measurement you can do using this kind of materials or this kind of sensors. So this is like something really important in the biology. It can measure temperature, electric field, magnetic field, radicals, all these things using this kind of sensors, quantum sensors. Okay. And again, like as in the introduction, people told that actually you can use NMR. I'm an NMR spectroscopist. So the idea is that why I am interested in that. See, the idea is that you can make an NV NMR. So the idea is that you just need a really small amount of material to do the NMR. Okay, and so the idea is that this is like something NV NMR, and you put your samples here, and the magnetic field produced by these can be used, we can measure and this is like the spectra. And the idea is that here you don't need a superconducting magnet, okay? Because you can use hyperpolarization, and then another thing is that you are not measuring with a coil, you are measuring the signal optically. The optical photon is way more higher energy than the radio photon. Okay, so the idea is that that's how the sensitivity improves, and then instead of using like a very huge amount of sample, we are using a very like femtomole sample, and we can able to see the spectra. For example, in biology, sometimes the proteins are very small. Okay, quantity is very small. So you can use such an instrument there, and basically you can measure an mass of that kind of sample. Okay. Now, diamond is like very hard to fabricate, and also like you have to, for creating a one NV center, you need two vacancies, then you have to put one nitrogen there. So it is little bit hard. So if you want to do some on demand, like you want to create some NV at a particular position, right now people have developed some techniques, but suddenly it is hard. Okay. But there are some alternate materials, for example, silicon carbide and organic crystals, and then this hexaboron nitrate. These also have similar kind of defects, okay? And I usually like working in these two materials, of course in ME also, and maybe I will share you some. So the similar kind of defect exists in a silicon carbide called silicon vacancy. So basically, if you have a silicon carbide, if you remove one silicon, okay, that there will be a silicon vacancy, and if you shine a light, it will also get polarized, and it can also, we can use the same thing, we can do measurement, all kind of thing, and silicon carbide is cheaper, and also you can make a very big wafer of it. Like making a diamond of this size, like 1 centimeter is really hard, like you can hardly make it. Okay, but this silicon wafer can exist in like in inches, like you can get 12-inch silicon wafer, silicon carbide wafer. So right now I think our government is also planning to in Andhra Pradesh, something they are doing, like they want to make a, because this silicon carbide is used in the electrical vehicles, EVs and everywhere. So we need it. This electronic, for example, your computer also have this silicon carbide CMOS and everything. So this is very important and well fabric. Its technology to build silicon carbide is like well established, and everything is like already matured. So all we need, this wafer is already available, and we just need to implant some iron in it, and we can create a vacancy. So this is very easy to make vacancy system. And I am working right now, like I have a project with IUAC Delhi, and there I am actually creating vacancies in the silicon carbide. And maybe next time when I come, I will show you my results also. So basic idea is that you can implant helium. So for example, if you want to create a vacancy at one particular position, so like if you want to select the depth, you can basically change the energy of the helium. Okay, then you will decide the depth, and you can control the XY position using like this mask. Okay, then you can create an array of this vacancy. So this is this, for example, if you see this plot, this is the plot I recorded, and these small dots are basically vacancies, and this for example this. So this is some like confocal setup, and you shine a laser, and then basically you can record a single photon, and this objective is on the piezoelectric stage, and you can move the piezoelectric stage, and you can scan the vacancies. All these dots are actually vacancies. Okay, so you can create the array of vacancies. Okay, and you can do sensing and also quantum computing and all these things, because it can act as a Q quad or qubit. Okay. So this was the something which I did in Germany, and it took me like 3 years to build this setup. Okay, and then I able to see the contrast, which is a very important parameter, and it's 6, and it is a shallow vacancies, and which is very useful for the sensing purpose. So the 6% contrast is huge, and then I really got interested, and now I want to extend this work, and right now I'm working in GNDU in my lab so that I can extend this work. Okay. Now let's come to the DAV organic crystals. Okay, so when when I was at Berkeley, I was in luckily chemistry department, so people are working with this organic crystal, and somebody told me that it can also behave the same way as the diamond. Then I thought I should also look into that. So then we actually start making this crystal, and the idea is that you can make this crystal in a lab. Okay, you don't need to buy it. You can easily make in your lab, and the size of these crystals can be like this diamond is like its price if you buy it from the market it will be like in lakhs, like 2 lakh, 4 lakh, 5 lakh. Special diamond it could be 4, 5 lakhs. Okay, and usually you will not get it here and the quality you want, but this big crystal you can make in your lab and it will hardly cost you like 50,000, or actual cost will be, the first time cost will be 50,000, but you can like later on if you find out the cost maybe like in few thousand rupees only. Okay, so this is the advantage. Okay, so that's why I got interested. So how to make it that? So first you have to purify your material. So there is a method called zone refining. So basically then this kind of setup you can make in your lab and heat it, and then the idea is that you can make multiple zones, and then after like sufficient long time doing this, and it is very slow, like you can see 30 millimeters, like 3 centimeter up and down in an hour, and you have to run it for like 70 days or 30 days continuously. Okay, slowly, and then you will see impurities. Then you get a pure this, you can cut it here, uh, and then you can pure the dot. Like this is a pentacene which have 5 rings. You can purify that material also, and then that this, because if you want to make a crystal, the one fundamental thing is purity. If your crystal is pure, okay, if your material is pure, and that is the like half step. Okay, like very important. If you don't have pure material, if your purity is bad, you will always get a bad crystal. Okay, or maybe you end up with a polycrystal. Okay, so this is like very important step, and then so after purification, you can add the doping, and you have to like put it in a furnace and move it slowly, like 2 millimeter per hour. Okay, then you end up with this crystal formation. Okay, but the idea is that all these things are feasible in a lab. Okay, but making a diamond in a academic lab is really hard. But this kind of crystal you can make. I made it in Berkeley, so it took long time, like 6 months. But yeah, eventually you will get some result. Then coming to the another property, like let us suppose you have this p-terephenyl crystal, organic crystal, and topped with a pentacene, which are 5 rings of benzene. And if you shine a light, it have this kind of energy level. So singlet excited, and some of the population go to the triplet state to the intersystem crossing process, and there this TX get more populated. And these are the actually dynamics which I simulated. And but here it is slightly different. If you apply a pulse, then the population, like in this TX state, goes to 75% of population go to this level only. Okay, and if you apply a long duration pulse, what happens that these states also get populated, and this TX get depopulated, and mostly you end up with a mix, like all have the same population. Okay, but slightly different. So this is like almost inverse. The energy levels are almost opposite to the what we have in LV. And this is the setup that I made to study this and to do the quantum sensing. So this is like a laser, pulse laser, and then you have a CW laser, and we actually couple these two beams, and then we basically shine this, and this is a very special dichroic mirror which allow to pass laser of 532 nanometer reflect and let pass the 600 or above nanometer light to transmit. Okay, so basically using this mirror, we can basically shine the light here on the sample, and then we collect the same photoluminescence from the sample and record it in this APD. Okay, and using the locking amplifier, depending upon the mode we want to use, we can basically record the spectra. of which we call ODMR. So these are the peaks, okay, of this ODMR. And the idea is that its line width is really small, it's like 1.9, and the docking is very high, which is like very, very difficult in MVs. Like because there, the idea is that in MV we are creating the defect, and in silicon also we are creating the defect. So there is a limit. Like if you create lot of defects, what will happen? You will amorphize the crystal. Okay, so the crystal will basically, if you want to create a defect in this wall, there is a limit. Okay, you cannot create, like you cannot remove all the bricks, then there is no wall. Okay, so but here the idea is that in this kind of stuff, here we are not creating, like we are not creating vacancies. Here we are putting a molecule. Okay, so this kind of system we can dock more. So if we dock more, we will get more signal. Okay, and this will increase the sensitivity. So that was the idea and motivation, which we can't do in actually defect-based systems. Okay. So this is the some simple characteristic of characterization. Like this is the ODMR spectra, and here is the sensing. Like if you sit on this position, and if you apply a very small magnetic field, you can see the change in the signal. Okay, and from there you will find the sensitivity. And right now means I sit on this and this transition and apply a magnetic field, and it is actually a magnetic sensing, and it is like giving us 0.6 microtesla per 0.6 microtesla per hertz. So this is a unit for sensitivity. And similarly for this transition XZ, we have 0.5 microtesla per square root hertz. Okay, so you know this thermal noise is order of microtesla. Okay, so this have a sensitivity of the thermal noise, but you can definitely enhance it. So there are some sensors. If you optimize your setup, this setup, and if you create a like very big sample, very big speed, like right now I am using a very small part of that. It's in the area is like few meter cube. But if I use the whole sample, then in principle I can enhance the sensitivity to the picotesla. But the idea is that you need a lot of sophisticated instrument. But certainly you can measure the picotesla at room temperature, which is itself a very big achievement, because right now you can use it for measuring the picotesla, but the idea is that you need liquid helium and it is at low temperature. But this kind of sensors can measure at the room temperature. So this is the motivation. Okay. Then there are some certain things like okay, so for example, if you continuously shine the laser, okay, so this is a plot to show that impact of the laser. So if you give a small pulse, you will see that the population in the triplet EX state is 76%, but as we increase, it goes like mix the system. So basically, here if you apply a pulse, you will get a very high population. Okay, so what we did basically, we actually mixed it here. Okay, like if we continuously illuminate the laser, so it gets mixed, and so the idea is that if instead of doing this CW ODMR sensing, if we go to the pulse ODMR sensing, we can get a higher sensitivity even with a small area. So that is the motivation. Another thing is that if you go to the low temperature, then there is a, even if you with a CW laser, you have some population difference there, and you can use that. Okay, so that's why in my setup we have a pulse laser also. So this is the experiment we did, and with a pulse laser. So this is a 65 nanosecond pulse I gave, and I able to see the 16% contrast, which is huge. Okay, and we certainly expected that based on this, like I measure Rabi oscillation, FID, T1, and all this characterization, and based on that, I estimated the sensitivity goes to nanotesla, like 4 nanotesla we can measure with this kind of sensor, which is a very nice number. Since my setup is not so optimized, but still we can really measure the nanotesla sensitivity. So this was a great result. Later, I use the same organic crystal for measuring the temperature. So this is the cryostat. So setup is modified, and then I change the temperature. And when you change the temperature, the heat start getting shift because of the temperature. So the idea is that in organic crystal, when we change the temperature, the lattice strain change, in the environment change, the magnetic field change around the fantasine, and due to that, this Odima peak gets shifted. Okay, because the zero field splitting change, and this change is actually tracked with the temperature and for example, for XZ transition, you can see this kind of thing. And also at one particular temperature, at 193 Kelvin, we see the phase change also. So this organic crystal phase from triclinic to monoclinic get changed. So this whenever there is a phase change, so there the system becomes really sensitive. So this particular regime have a very high sensitivity. So in principle, we can make a sensor by utilizing exploiting the phase change property, and this sensitivity will be huge. Okay, so this is the material which actually shows some phase transition also. So that's why it is very important. And then I move to the pressure sensing also. So basically, I put a material in the pressure chamber and apply the pressure like just with a normal pump. Okay, which you use for filling the air in a tire. It's the same pump. Okay? And the rest of the setup is same. And when we apply the pressure, again this transitions change, and you can see these peaks are changing. And these peaks, because the organic crystal is very soft, so it is very pressure sensitive. And you know, in diamond is very hard, so it is actually not so sensitive as this crystal. And due to that, this was like a very nice result. And so the idea was that originally when I started this experiment, it was I want to do some pressure temperature sensing. But when I actually use this cryostat, I have to pull out the air from it, okay, to create a vacuum so that I can go to the low temperature. When I went to the vacuum, my peak got shift. Then I realized that pressure is also impacting. Okay, and later on we found that temperature results were not so good, but the pressure result was so good. And this paper last week got accepted in Nature publication. Okay, because the pressure sensitivity was so high. So you can see like in here, this is the very important parameter. For XZ it is 1800, and for NB it is 1.46. So it's like 1200 times better sensor than NB organic. So it's very sensitive because the lattice is soft. So the idea is that we can put this kind of sensors in the tissues, and here we can monitor the pressure. So for the biology purpose, this is a very tremendous result. For example, right now I'm writing a project on microplastic, which is very common nowadays in the plant also, especially in, like there are some people who want to grow plant in the water, and there are a lot of microplastic get up. And then you want to track like what is the stress it is creating at that particular time and place. So you can use this kind of sensors to monitor the pressure. So this is the like application. And yeah, so in conclusion, like so organic crystal can be used as a quantum sensor. It is low cost and very scalable platform as to the ND platform, and high sensitivity. So as I told, it is 1200 times better pressure sensor for the small pressure range. Certainly it will break if you give a very high. So ND will not break. So where you want to measure a high pressure, you should use ND. So it's like a complementary. You can use one sensor at one place where pressure is very high, and where the pressure is very low, it is very insensitive. But you can use the organic. And it is again at room temperature, and so it have a sufficient coherence time. So we can basically do the magnetic AC field and DC field sensing, and also like this synthetic tunability and scalability. So unlike defect, as I told, like you can increase the doping. So are you able to get a 0.3%? But right now, when I left the Berkeley, we found a material where we can do 30% doping. And right now we are working on that. And so basically, so this organic state in the quantum sensing is booming. And so idea is that it is cheap, and also like whatever the disadvantage in the enemies, it is covering. So it is kind of complementary material to the enemy. That way. And of course, like we can use this material for a number of things like hyperpolarization, and you can make a use of hyperpolarization to create a sensors based on the nuclear spins, because the nuclear spins have a very low magnetic moment, but you can first polarize the electron of the organic crystal, pentacene molecule, and transfer that polarization to the nucleus in the crystal, and like protons, and then you can use that as a sensor which have a long coherence time. So these kind of complex quantum sensors can also be used. Okay? Thanks.
The session is now open for discussion. If you have any questions, you can ask.
Somebody looking for alternatives can be that then you come to organic research. So is there a particular realistic quantum advantage from these organic crystals at room temperature, or cryogenic must be more fundamental?
No, no, like whatever experiment I show you, that apart from temperature sensing, because for temperature sensing you have to apply some temperature. Otherwise, most of the experiment I have done at room temperature.